The Art of Building Chat GPT Andrej Karpathy's Implementation, 2025 to 10 to 16. How to read this book. This guide is written to be spoken aloud. Imagine listening to a thoughtful conversation about how modern artificial intelligence systems work. We focus on ideas, intuitions, and concepts rather than code syntax or mathematical formalism. When we mention code, we describe it conversationally. For instance, instead of seeing something cryptic like torch.optim.atom, we'll simply say that the PyTorch library provides this function through its optimizer module, as if we were explaining it to a friend over coffee. You already know transformers and vision transformers. You understand gradient descent, momentum, and learning rate schedules. You have experience with optimizers, so we won't dwell on the absolute basics. Instead, we'll explore what makes this particular implementation elegant and why those specific choices matter. We'll uncover the philosophy behind the design. We'll walk through the journey of training an AI from random noise to intelligence, and we'll understand not just the what but the why. This book is written in the spirit of Richard Feynman. We believe that if you cannot explain something simply and beautifully, then you don't really understand it. So we explain everything that way, with clarity, with wonder, with respect for your intelligence. The big picture: what is NanoChat? Imagine you want to build ChatGPT, not the $100 billion version that requires entire data centers and armies of engineers. Something you can understand. Something you can train yourself in just a few hours for about $100. Something that fits in your hands, runs on a single machine, and teaches you the complete story of how modern language models work. That's NanoChat. Andrej Karpathy, the director of AI at Tesla and creator of the legendary NanoGPT, built this system to prove something important: that you don't need complexity to create something powerful. You need clarity, elegance, and ruthless focus on the essential. Every line of code in NanoChat has a purpose. Every design choice has a reason, and together they create something truly magical. The system is complete. Take raw text from the internet, tokenize it into numbers the model can understand, train it to predict the next word, teach it to handle longer contexts, fine-tune it for conversation, use reinforcement learning to reward good behavior, evaluate it on diverse tasks, serve it through a web interface so you can chat with it like you would chat GPT. All of this fits in about 8,000 lines of Python code across 45 files. No bloat, no framework, just the essential truth of how to build an intelligent system. Think of it like watching a master craftsman. You're not just seeing the final painting. You're watching how the canvas is prepared, how colors are mixed, how each stroke is applied. You understand the entire creative process. And at the end, you have a masterpiece you can modify and make your own. The journey from words to wisdom. Before we dive deep, let us map out the entire pipeline. Understanding the big picture first makes everything else click into place. The journey begins with data. NanoChat uses FineWeb, a massive collection of high-quality text from the internet, carefully curated and cleaned. This is the raw material. Billions of words, billions of ideas, all waiting to be learned. Next comes tokenization. This is the translator between human language and mathematics. Words are continuous, flowing, infinite. Neural networks work with integers. We need a bridge. Tokenization breaks language into small pieces called tokens. A word might be 1 token or 3. A number might be 2. The algorithm learns the right granularity automatically. This is one of the most ingenious parts of modern language modeling, and we will explore it in depth. Then comes the transformer model. At its heart is self-attention. Imagine you are reading a sentence and encounter the word it. What does it refer to? You look back through the sentence, weighting each noun by how likely it is. Self-attention does exactly this. The model learns what matters by looking at all previous context and deciding which parts are relevant right now. The training happens in stages. Each stage teaches the model something new. In the first stage, pre-training, we teach the model the patterns of language itself, how language flows, how ideas connect. In the second stage, mid-training, we teach it to handle longer documents. In the supervised fine-tuning stage, we show it examples of conversations. In the reinforcement learning stage, we reward it for better responses. Finally, we evaluate and deploy. Throughout, we measure progress using beautiful metrics. Bits per byte tells us how surprised the model is by text it has not seen. Benchmark tests measure how well it does on math, coding, reading comprehension, and world knowledge. These numbers tell us if our approach is working. And spoiler alert, it is. What emerges from this pipeline is remarkable, a system that understands language and can help you solve problems. Philosophy of design. Before we examine the parts, we need to understand the philosophy that guides the whole. NanoChat is not a random collection of choices. It is the result of careful thinking about what matters and what does not. Simplicity as a feature. The first principle is simplicity, not the simplicity of something naive, but the simplicity of something essential. Every line of code has been asked, do we really need this? Will it make the system clearer or more confusing? This leads to surprising design decisions. There are no configuration frameworks, no macro-like builders, no runtime dependency injection. Just plain Python variables at the top of scripts that you can see and modify immediately. There are no giant classes that try to do everything. Instead, small, focused modules that do one thing well. The tokenizer tokenizes, the model models, the data loader loads data. Each can be understood in isolation. This is radically different from modern machine learning frameworks which often prioritize flexibility and extensibility. NanoChat prioritizes understanding. This is a deliberate choice, and it is the right one for a learning project. Ideas over implementation. The second principle is that ideas matter more than engineering cleverness. Modern deep learning research is full of small innovations, rotary embeddings, query key normalization, multi-query attention, orthogonalized momentum in muon. Each of these is an idea. Each one is motivated by a deeper understanding of what works and why, and each one is worth understanding deeply. When you read the code, you see these ideas implemented as clearly as possible, not with performance hacks, not with clever tricks. Just the idea implemented straightforwardly so you can understand it. This is why the code can be small. It is not doing unnecessary things. It is implementing the essential ideas and nothing more. Pragmatism wins. The third principle is pragmatism. When there is a choice between purity and practicality, pragmatism wins. This shows up everywhere. There are two tokenizers, one flexible for training, one fast for inference. Not one tokenizer that tries to do everything and does neither well. Two implementations, each optimized for its purpose. There are two optimizers, Adam W for embeddings, muon for transformers. Not one optimizer trying to work for everything. Each optimizer for what it does best. The code uses both Python and Rust where each is appropriate. Configuration via command line overrides mixed with default variables, whatever works. This pragmatic approach prevents the code from becoming dogmatic. It can adapt to reality rather than forcing reality to fit the design. Accessibility is paramount. The fourth principle is accessibility. This project exists to teach. Every design decision asks, will this make it easier for someone to understand the system? This is why there is no complex metaprogramming, no dynamic class construction, no layers of indirection. These might make code more flexible or powerful, but they make it harder to understand. This is why there are clear module boundaries but not rigid boundaries. You can follow how data flows through the system. You can understand how training works without being lost in abstractions. This is why the code is documented not with extensive comments explaining what each line does, but with comments explaining why things are the way they are. The code itself should be self-explanatory. These four principles, simplicity, ideas, pragmatism, accessibility, shape everything about NanoChat. They are why you can read and understand this codebase as a single person. They are why you can modify it and make it your own. How the code is organized, philosophy and structure. Before we examine individual pieces, let us step back and understand the bigger picture. How the code is organized, why it is organized that way, and what philosophy guides every choice. The philosophy of minimalism. If you have worked with modern machine learning frameworks, you might expect NanoChat to be sprawling. Hundreds of configuration options, deep inheritance hierarchies, factory patterns, base classes, abstract interfaces, dependency injection, layers upon layers, none of that is here. NanoChat follows a principle: keep everything as simple as possible, not simple in the sense of dumbed down, but simple in the sense of direct, clear, transparent, understandable. You can read this code, you can hold it all in your head at once. This decision shapes everything. Every file has a clear purpose. Every function does one thing well. Every class, when a class is used, has a clear reason to exist. When you wonder why something is the way it is, you can read the code and find out. For example, there are no massive configuration objects. Instead, training scripts have a section at the top with user settings, plain Python variables, depth equals 20, max sequence length equals 2048, and so on. To change them, you edit the script or pass command line arguments. No YAML parsing, no nested dictionaries, just straightforward variables you can see and understand immediately. Dependencies are minimal. PyTorch for neural networks. Hugging Face tokenizers for one approach to tokenization. A Rust tokenizer for speed. That is it. No exotic libraries. No packages that promise convenience but hide complexity underneath. The style consistently favors clarity over cleverness. If you encounter a choice between a concise Python idiom and a slightly more verbose but obvious approach, the code almost always chooses obvious. This is not a bug. It is a feature. The folder structure, organization by concern. Let us walk through the directory structure and understand what lives where and why. The root directory. At the root you have the main entry points and project files. Speedrun.sh and run1000.sh are shell scripts that orchestrate the entire training and serving pipeline. They are the main thing you run. They show what happens when you train a model from start to finish. pitproject.toml and uv.lock are Python dependency files. They tell you what packages are needed and what exact versions to use. uv is a fast package manager that replaces pip. It is included because it makes the project reproducible. The same files run the same way everywhere. readme.md is the entry point for humans. It explains what the project is, how to run it, and where to find help. The book directory is where you are now, documentation for understanding, for learning, for contemplation. The NanoChat directory, the core system. This directory contains the essential machinery. Every file here handles a specific responsibility. Every file is a module. Tokenizer.py handles the transformation from text to tokens and back. All tokenization logic lives here. 2 implementations actually. One flexible for training, one fast for inference. GPT.py is the transformer model, the attention mechanism, the feed-forward layers, the initialization, generation. It is arguably the most important file in the system, probably only a few hundred lines, beautiful code. Dataloader.py is the interface between raw data and the training loop. It streams data, it tokenizes it, it yields GPU tensors ready to go. Dataset.py handles downloading and organizing training data from Hugging Face. It manages shards and batching at a high level. Adamwa.py is a specialized version of the Adam optimizer, modified for distributed training across multiple GPUs. Muon.py is a custom optimizer designed specifically for large transformer matrices. It treats matrix parameters specially, orthogonalized momentum, more efficient for this specific problem. Common.py contains utilities, distributed training setup, colored logging, convenience functions, the glue that holds things together. Checkpoint.manager.py handles saving and loading models during and after training, so you do not lose your progress, so you can resume. Loss.eval.py computes bits per byte, a vocabulary-independent perplexity measure. How surprised is the model really? Not by the number of bits used to represent a token, but by the actual bytes of information. Core.eval.py runs the benchmark evaluation, testing the model on diverse tasks. Math, code, reading, knowledge. Engine.py handles inference. It manages the key-value cache for efficient generation. It handles streaming output, tool use, sampling. Execution.py provides a sandboxed environment for running code. When the model wants to execute Python, this module ensures it cannot do anything dangerous. No file deletion, no network access, just pure computation. Configurator.py is a simple configuration system. It lets you override default settings via command line arguments or config files. Clean and minimal. Report.py generates reports. Summaries of training runs with metrics, hardware info, costs, everything you need to understand what happened. UI.html and logo.svg are static files for the web interface. The pretty front end where you chat, the script's directory entry points. These files are the scripts you run to do specific tasks. Each script is a complete pipeline stage. Base.train.py trains the base model. It is the pre-training loop. Random weights. Language modeling, gradient descent, checkpoints saved. Base.eval.py evaluates the base model on the core benchmark. How well does it predict? What score does it get on math, on code? Mid.train.py extends training to longer sequences. Take the base model and teach it to handle longer context. Chat.sft.py fine-tunes on conversation data. Supervised fine-tuning, show it good examples, let it learn from them. Chat.rl.py applies reinforcement learning, generate multiple responses, reward the good ones, improve. Chat.eval.py evaluates the chat model. How good at conversation is it now? Chat.cli.py is an interactive command line chat interface. Type a message, get a response, learn. Chat.web.py is a web server that exposes the model via a REST API. It looks like ChatGPT. You can use it in a browser. Each script has a clear purpose. Each script can be understood independently, though they share common utilities from the NanoChat package. The Rust directory, fast tokenization. Tokenization has two implementations. Hugging Face tokenizers is flexible and powerful for training, but for inference speed matters. So there is a Rust tokenizer here that is much faster, orders of magnitude faster. This separation reflects pragmatism. Use the right tool for each job, train with flexibility, serve with speed, the tasks directory evaluation data. These files define the evaluation benchmarks. ARC, GSM 8K, Human Eval, MMLU. Each task has a structure. Training examples, test examples. Evaluation logic, a unified interface. The tests directory verification, just a few tests, mostly for the tokenizer, not exhaustive but enough to catch major breakages, enough to know things still work. The stylistic choices, why code looks the way it does. Now let us understand the broader choices that shape how the code reads and feels. Functions over classes. When is something a class? When it needs state that persists across multiple calls. The engine class maintains a key value cache, that is persistent state, so it is a class. The GPT model is a class because it has learnable parameters and needs to maintain them across training steps. But many things are just functions. The loss evaluation is a function. The data loading loop is a function. The evaluation logic is a function. This is the opposite of typical object-oriented design where you would create a data loader class or an evaluator class. Here, if it is functional, it is a function. If it needs state, it becomes a class. This makes the code feel lighter, more direct. Tokenization, the bridge between language and numbers. Let us begin with tokenization, the foundation of everything. Human language is analog, it flows, it has infinite possibility. Neural networks are digital, they work with integers. Tokenization is how we make this translation, and it is more important than most people realize. The core concept. Imagine teaching someone to read a language they do not know. You cannot start with meaning. You start with the alphabet. You learn that certain symbols go together. You notice patterns. Over time, you recognize words, then phrases, then ideas. Neural networks need something similar. They cannot work with raw text. They need discrete, manageable pieces. That is tokenization. But here is the puzzle. How big should these pieces be? If tokens are single characters, you would need many tokens to represent a word. A GPU could only process a few words at once. If tokens are words, there are too many. English has hundreds of thousands of words. Many are rare. Many are made up. Many are typos. Your vocabulary explodes. The answer, tokens, should be at some middle level. A word might be one token or two or three depending on frequency and length. Byte pair encoding. Byte pair encoding, or BPE, is an algorithm that finds this middle ground automatically. Here is how it works step by step. Start with raw bytes. Text at its most basic. Every character is represented as its byte value. You have a vocabulary of 256 tokens, all possible bytes. Now find the most common pair of adjacent tokens. In English text, perhaps the pair ET is very common at the end of the word the. Merge this pair. Create a new token representing et. Update your vocabulary. Scan the text and replace all instances of this pair with the single new token. Repeat. Find the next most common pair. Merge it. Add it to the vocabulary. Repeat until your vocabulary reaches your target size, say 50,000 tokens. What emerges? A hierarchy. Single bytes for rare characters, common bigrams as tokens, common trigrams, common words. The algorithm naturally learns the right granularity because it is driven by frequency. This is elegant. You do not handcraft a vocabulary. The algorithm finds one automatically tailored to your specific data. Special tokens, but BPE gives you only the tokens that appear in your data. You need more. You need tokens that convey structure and intent. That is where special tokens come in. Consider a document. Where does it start? In traditional language models, just random tokens, but in fine-tuned models you want the model to know when it is starting a new document. So you add a special token, beginning of sequence or BARS. When you train on a conversation, you need to distinguish user messages from assistant messages. Special tokens mark these boundaries. User start, user end, assistant start, assistant end. When the model wants to use a tool like Python, special tokens mark this. Python start, Python end, output start, output end. These tokens have no inherent meaning. Meaning is learned, but by using them you are giving the model explicit structure. You are saying, pay attention to these boundaries, they matter. Masking. Here is a subtle but crucial concept. Not all tokens should be trained on equally. Consider a conversation. A user asks a question, then an assistant replies. During training you want the model to see the user message but not predict it. The user message is context. Only the assistant response should be predicted. This is implemented through masking. Each token is marked as either train on this or do not train on this. When computing loss, ignored tokens contribute 0. The model learns to predict assistant responses, not to reproduce user messages. This seems simple, but it is powerful. It teaches the model the asymmetry of conversation. Users provide context, assistants provide responses. This shapes what the model learns to do. 2 implementations. The code implements tokenization 2 ways. The first, using Hugging Face tokenizers, is flexible. You can train a tokenizer, save it, load it. You can inspect what tokens exist. You can modify the process. It is designed for training. The second, using Rust with TickToken, is fast. For inference, you are tokenizing user messages on the fly. Speed matters. A Rust implementation is orders of magnitude faster. This duality reflects pragmatism. Use each tool where it shines. Train with flexibility. Serve with speed. The transformer, a masterpiece of simplicity. Now we reach the heart of NanoChat, the transformer model itself. This is where the magic happens. What is a transformer? A transformer is a machine for learning patterns in sequences. It takes a sequence of tokens, represented as vectors, and produces predictions. The fundamental operation is called self-attention. Here is the intuition. Imagine you are reading a sentence. You see a pronoun, it. What does it refer to? You look back through the sentence, weighting each noun by how likely it is to be the antecedent. Which noun makes sense? That is what self-attention does. The model sees all previous tokens in a sequence and learns to weight them. Which tokens matter for understanding the current token? The attention mechanism learns to figure this out. This is powerful because context is crucial for language. The meaning of a word depends entirely on what came before. Why transformers? Before transformers, recurrent neural networks were dominant. RNNs process sequences one token at a time, maintaining hidden state. The previous hidden state influences the next. But RNNs have a problem, gradients. When you compute how to improve parameters, gradients flow backward through time. In long sequences, gradients get multiplied many times. They either vanish or explode. Transformers solve this by not being recurrent. All tokens in a sequence are processed in parallel. Attention directly connects distant tokens. Gradients flow directly without many multiplications. Training is faster and more stable. This is why transformers revolutionized language modeling. The building blocks. A transformer is built from simple pieces. Embeddings convert discrete token IDs to continuous vectors. A lookup table, essentially. Token 256 maps to a vector. Token 257 to another. The embedding space is learned during training. Self-attention computes relevant scores between all pairs of positions. It learns what each token should pay attention to. Feed-forward networks are simple nonlinear functions applied to each position independently. They add representational power. Residual connections add the input to the output of each layer. They help gradients flow and stabilize training. Normalization stabilizes signals. It keeps activations from growing too large or shrinking too small. Stack these together and you have a transformer block. Stack many blocks and you have a transformer. The GPT class in GPT.py implements all of this. Rotary embeddings. Traditional transformers use sinusoidal position embeddings. You add a sinusoid to each token based on its position. The frequency varies by dimension. This is elegant but indirect. Rotary embeddings, or RoP, are different. Instead of adding position information, you rotate the query and key vectors. Rotation is a geometric operation. It does not change magnitude, only direction. Why does this work? Because rotation by different amounts encodes position. Token at position 5, rotated by 5 units, is different from token at position 10, rotated by 10 units. When you compute attention, these rotations naturally encode relative position. This is better because it is more direct and theoretically grounded. But practically, it also trains faster and generalizes better to longer sequences than static position embeddings. This is an innovation that appears in modern language models, and NanoChat includes it. Multi-query attention. Standard attention in transformers has many heads. Each head has its own queries, keys, and values. This allows the model to attend to different types of information in parallel, but keys and values are redundant. All query heads are attending to the same keys and values, just from different angles. Multi-query attention removes this redundancy. All query heads share the same keys and values. This reduces parameters and memory. It also speeds up inference. Does this hurt performance? Barely. You lose some representational capacity, but not much. The speed-up is worth it. This is the kind of trade-off Carpathy made throughout, slightly less capacity for significantly better efficiency. Query key normalization. Before computing attention, the dot product between queries and keys normalize both. This stabilizes the mechanism. Why? Because without normalization, the dot products can grow very large. Large dot products lead to sharp attention, paying attention to one token and ignoring others. Normalization keeps things balanced. This is a simple trick, but it often improves training stability and performance. These small touches are what separates a model that trains cleanly from one that diverges. The unembedding. At the end of the transformer, you have hidden states, vectors. You need to predict the next token. This requires projecting back to vocabulary space. 1 score per passable token. Most models tie the unembedding to the embedding. They use the same matrix transposed. This saves parameters. NanoChat keeps them separate. Untied weights. This costs more parameters but gives the model more flexibility. The trade-off is worth it. A bit more capacity for a model of this size. Initialization. When you initialize a neural network randomly, the choice matters hugely. For linear layers, use chiming initialization. This ensures that gradients have roughly unit variance, no matter the layer depth. Gradients do not vanish or explode early in training. For embeddings, use normal initialization. For the final layer, zero initialization. This makes the model initially predict uniformly over all tokens, which is reasonable. These choices are not arbitrary. They are based on theory. Analysis of how information and gradients flow through networks at initialization. Training the patient art of teaching. Now we move to the act of training, turning a randomly initialized model into something that knows language. The training loop. The training loop is conceptually simple. Take data, compute gradients, update parameters. For each step, get a batch of token sequences. Forward pass, run through the model, get predictions. Compute loss, cross-entropy between predictions and actual next tokens. Backward pass, compute gradients of loss with respect to all parameters. Optimizer step, update all parameters based on gradients. This is classical gradient descent, but the details matter. Gradient accumulation. Training a language model requires large batches to use GPUs efficiently. A batch of 32 sequences times 2,000 tokens is 64,000 tokens per step. Larger is better, but it does not fit in memory. The solution, gradient accumulation. Do multiple smaller forward-backward passes, accumulating gradients, then one optimizer step using the accumulated gradients. To the optimizer, it is as if you did one large forward-backward on a huge batch. In reality, you did it in smaller chunks. This lets you use batches that would otherwise exceed memory while maintaining the benefits of large batch training. Learning rate scheduling. The learning rate is not static, it follows a schedule. Warm-up. The learning rate increases from 0 to its target over the first few steps. Why? Because the model is initially random. Large gradients early on could cause divergence. Gradually increasing the learning rate prevents this. Constant. After warm-up, the learning rate stays constant during the main training phase. This is where most learning happens. Cool down. Near the end of training, the learning rate decays following a cosine curve. This lets the model settle into a good minimum without overshooting. This schedule is based on empirical observation. It works better than a constant learning rate. The base train.py script implements this. 2 optimizers. NanoChat uses 2 optimizers, ADAM-W for embeddings and muon for transformer matrices. This is a design choice that comes from research on what works best for each type of parameter. ADAM-W is the standard optimizer in deep learning. It maintains first and second moment estimates of gradients, using these to scale step sizes adaptively. It is robust and works well. It is ideal for embeddings which are fragile and need careful tuning. Muon is specialized for matrix parameters. It orthogonalizes momentum, inspired by natural gradient methods. For large models, this often converges faster than Adam W. The idea is that for weight matrices you want to take steps that are orthogonal, respecting the geometry of the parameter space. The learning rates are different and scaled carefully. The embedding learning rate is lower. The scaling respects the dimensionality of parameters. Smaller parameters get smaller learning rates. This is implemented in the GPT.py file where optimizers are set up. Distributed training. With one GPU, training is slow. 8 GPUs, it is 8 times faster, with careful coordination. Each GPU has its own batch. It computes gradients on its batch. Gradients are averaged across all GPUs using collective operations. The optimizer step is applied on all GPUs simultaneously, keeping parameters synchronized. There is a variant called ZRO2 used here. Instead of each GPU storing all parameters and all gradients, parameters are partitioned. Each GPU stores a shard. During the backward pass, gradients are reduced across GPUs. During the optimizer step, each GPU updates its parameter shard. Then all parameters are gathered back. This reduces memory usage while keeping computation well distributed. Evaluation during training. Every few hundred steps, training pauses. A validation batch is evaluated. Metrics are computed. Loss, bits per byte, may be a benchmark evaluation. Why pause to evaluate? Because you cannot trust training loss. Training loss can decrease artificially if the model is overfitting. Validation metrics tell you if the model is really learning generalizable patterns. These metrics are logged. Over time they paint a picture. Is learning stable? Is the model improving? Is there evidence of overfitting? Tool use. During training, if the model generates a Python start token, the system collects tokens until the Python end token, decodes them into code, and executes the code in a sandboxed environment. Why? This teaches the model to use tools. If the model wants to verify an answer or compute something, it can. The result is fed back into the model as part of the context. This is optional during training and only during certain phases, but it is powerful. It teaches the model to break tasks into subcomponents. Inference, generating responses. Training is just the first half. Once trained, the model needs to be used. The challenge. A trained model can predict the next token given all previous tokens. During inference, you start with a prompt and generate tokens one by one. But there is a problem. To predict each new token, you need to recompute attention over all previous tokens. If you have 2,000 previous tokens and need to generate 100 more, that is recomputation. Exponential waste. This is what makes naive generation slow. The key-value cache. The solution is the key-value cache. Here is the insight. During attention, you compute keys and values from all previous tokens. These do not change as new tokens are added. You can cache them. When a new token arrives, compute its key and value. Add these to the cache. Compute attention using the full cache. All previous keys and values stay the same. This transforms attention from quadratic in sequence length to linear. Instead of computing n squared dot products for a sequence of length n, you compute n new dot products. New token against all previous tokens. This speedup is crucial. It makes interactive generation possible. Without the cache, your model would feel laggy and slow. With it, responses stream out at human-readable speed. The KV cache class in engine.py implements this. It maintains the cached keys and values for each layer. As generation progresses, the cache grows and each new token is quickly scored against everything that came before. Prefilling and decoding. There are two phases to generation. Prefilling, you have an initial prompt. Feed it through the model entirely in one forward pass. Build the cache as you go. This is efficient because you can batch the entire prompt. Decoding, generate one token at a time. Use the cache, much faster because you are not recomputing. This two-phase approach is elegant and efficient. Modern language model serving systems use exactly this pattern. Sampling. Given the model's predictions, largets over the vocabulary, how do you pick the next token? If you always pick the highest probability token, responses are deterministic and repetitive. Instead, sample. Convert largets to probabilities. Sample according to this distribution. This adds variety. Temperature controls the sharpness. High temperature makes the distribution softer, more diversity, less predictable. Low temperature makes it sharper, more predictable, less diverse. Temperature 1 is neutral. Top K sampling restricts to the K most likely tokens. This prevents the model from generating unlikely tokens. It is a practical improvement over plain sampling. Together, these make generation feel more natural and varied. Tool use during inference. If the model generates a Python start token during generation, the system interprets what follows as Python code until the Python end token. This code is executed but carefully. It runs in a subprocess with strict resource limits, memory limit, CPU time limit, no file system access, no network access. Many dangerous functions are disabled. This lets the model use Python as a tool for computation while preventing it from doing damage. Supervised fine-tuning, teaching conversation. After pre-training on general text, the model knows language. Now we teach it to be a helpful assistant. What is fine-tuning? Fine-tuning takes a pre-trained model and trains it further on a specific task. In this case, the task is conversation. We show the model examples of good human-assistant conversations and train it to predict the assistant responses given the user messages. The training loop is the same as before. Forward pass, compute loss on the assistant tokens, backward pass, optimizer step, but the data is different. Instead of general text, we use conversation examples, the data mixture. NanoChat fine-tunes on a mixture of tasks. It uses ARC, GSM8K, Smalltalk, and other benchmarks. Each task has conversation examples. ARC provides reading comprehension. GSM8K provides math reasoning. Smalltalk provides general conversation. By mixing multiple tasks, the model learns to handle diverse problems. It learns to recognize when a question is mathematical versus reading comprehension. It learns to apply the right type of reasoning. Masking and loss. Here is where masking becomes crucial. During fine-tuning, you compute loss only on the assistant tokens. User messages are not predicted. This teaches the model that its job is to generate helpful responses, not to reproduce user input. The masking is implemented in the conversation rendering. Each example is converted to token IDs with a mask. During loss computation, masked tokens contribute 0. The model only learns from the tokens it is supposed to predict. Learning rates during fine-tuning. The learning rates during fine-tuning are typically lower than during pre-training. Why? Because the model is already well trained. Large steps could cause it to forget what it learned. Smaller steps let it adapt to the new task without catastrophic forgetting. The chat sft.py script sets these learning rates carefully. They are tuned empirically through experimentation. Different layers might even have different learning rates, though in this implementation they are shared. Reinforcement learning, alignment with human values. After fine-tuning, the model is good at conversation, but it might not always give the best answers. This is where reinforcement learning comes in. The concept, reinforcement learning optimizes based on reward. Instead of predicting the next token given a human-written example, the model generates several possible continuations. These continuations are scored, and the model is rewarded for better continuations and punished for worse ones. In NanoChat, the task is GSM8K, math reasoning. For each problem, the model generates multiple solutions. Each solution is checked. If the final answer is correct, the model gets a reward. If the final answer is wrong, the model gets a penalty. The model learns to generate more solutions that lead to correct answers. On-policy reinforcement learning. The implementation uses on-policy reinforcement learning. This means the model generates samples, we compute rewards, and we update the model on those samples. Then we generate new samples. We do not replay old samples. Why on-policy? Because during generation the model is changing. Samples generated by an old version of the model might not be appropriate for training the new version. On-policy keeps the data fresh. GRPO and advantages. The algorithm used is similar to GRPO, Group Relative Policy Optimization, but simplified. Instead of complex trust regions and KL penalties, the implementation uses something simpler. For each sequence, you compute the reward. Then you compute the advantage, the reward minus the average reward for that batch. Advantages center the rewards. This lets the model learn which of its completions are better than average and which are worse. The loss is computed per token. Token-level advantages means the model learns which tokens in a good completion are important. Multiple samples. For each problem, the model generates multiple solutions. Maybe 16 solutions for each problem. The model sees which ones are correct, which ones are wrong. It learns from this diversity. This is powerful because the model learns that there are multiple paths to the right answer. It learns to explore different reasoning strategies and understand which ones work. Exploration and temperature. During RL, the generation temperature is high, maybe 1.0. This encourages exploration. The model tries different things. It does not fall into the trap of generating the same response every time. This is different from deployment, where you might use lower temperature for more predictable responses. During training, exploration is valuable. Evaluation framework. How do we measure if our model is learning? NanoChat uses a comprehensive evaluation framework, bits per byte. The primary metric during pre-training is bits per byte. This measures how surprised the model is by unseen data. It is vocabulary agnostic, useful when comparing models with different tokenizers. Bits per byte is computed by taking the cross-entropy loss and converting it to a logarithmic measure. The formula is bits per byte equals loss divided by log of 2, then divided by the average number of bytes per token. Lower bits per byte is better. It means the model is less surprised by unseen data, which means it has learned the patterns of language better. The core benchmark. Then there is the core benchmark. It includes diverse tasks: reading comprehension, math reasoning, code completion, world knowledge. Each task has multiple choice questions, or fill-in-the-blank questions. For multiple choice questions, the model is shown each possible answer as a continuation. The model predicts which continuation has the lowest loss. That is the model's answer. Accuracy is measured. For fill-in-the-blank questions, the model is asked to predict tokens in a blank given the prefix and suffix. Accuracy is measured. These evaluations run distributed across GPUs. Each GPU handles a subset of examples and results are gathered at the end. This is efficient and lets you evaluate large models quickly. Specific benchmarks. ARC is reading comprehension. GSM 8K is grade school math, multi-step reasoning. Human eval is code completion. MMLU is world knowledge across multiple domains. By testing on all of these, you get a holistic picture of the model's capabilities. You can see where it is strong and where it struggles. Few-shot evaluation. The evaluation is few-shot. The model is shown a few examples of each task type before being evaluated on new examples. This tests whether the model can quickly adapt to a new task. This is different from fine-tuning. In few-shot, you are not updating the model. You are just showing it examples and seeing if it can learn from context alone. This is a harder test and more aligned with how you would use the model in practice. The web interface, making it talk. Finally, the model needs to serve users. Architecture. NanoChat includes a web interface built with Fast API, a Python web framework. The backend has a pool of worker processes, one per GPU. When a request comes in asking for chat completion, we acquire a worker, build up the conversation state, previous messages plus the new user message, and stream tokens back to the client. The streaming is done asynchronously, sending events to the browser in real time. This makes the interface feel responsive and alive. The front end. The front end is simple HTML and JavaScript. You type a message, hit enter, and watch the model's response appear word by word. It feels like ChatGPT. There is no magic here, just clean, understandable code. Concurrency. The system can serve multiple requests concurrently by round-robining across GPUs. If a request takes a second, and you have 8 GPUs, you can serve 8 requests per second from a single machine. This is not massive scale, but it is serviceable for a single machine. The complete pipeline in practice. What happens when you run the speedrun script? First, setup. We ensure Python dependencies are installed using UV, a fast package manager. We initialize weights and biases for logging if desired. Second, evaluation bundle. We download benchmark data so we can evaluate the model. Third, data preparation. We download training shards from Hugging Face. This happens in the background while other steps proceed. Fourth, tokenizer training. We train the tokenizer on the downloaded data, building a vocabulary. Fifth, base training. We train the model from random initialization on the full training set. This takes most of the time. We apply pre-training with a learning rate schedule, evaluating regularly. Sixth, base evaluation. We run the model on benchmarks to see its baseline capability. Seventh, mid-training. We take the trained model and train it further but on longer sequences. This teaches it to handle more context. We use positional interpolation to extend the context window. Eighth, supervised fine-tuning. We take the mid-trained model and fine-tune it on conversation examples. This teaches it the patterns of dialogue. Ninth, further evaluation. We test this fine-tuned model. 10th, optional reinforcement learning. We can reward the model for better responses using reinforcement learning. This is done on math reasoning tasks. Finally, serving. We start a web server and expose the model. You can talk to it through a chat interface. The entire process takes 4 hours on 8H100 GPUs, costing about $100 in cloud compute. This is remarkable. A functional language model for the cost of a nice dinner. Diving deep, technical implementation of core functions. Now let us talk about the code in detail. We will walk through the key functions and classes, understanding not just what they do but how they do it and why they are structured the way they are. This is for those who want to understand the implementation fully. The GPT model class. The GPT class in GPT.py is the heart of the system. It extends torch.nn. module. PyTorch is base class for neural network models. The initialization takes a GPT config object that specifies all hyperparameters: sequence length, vocabulary size, number of layers, number of heads, embedding dimension. These are not hard-coded, they are parameters. Inside initialization, the model builds several things. First, the token embedding layer. This is a lookup table. You give it token IDs, you get back vectors. The embedding is initialized with normal initialization. Next, the position embedding for rotary embeddings. This is pre-computed. For a given sequence length, you compute the cosine and sine values needed for rotation. These are pre-computed because they do not change, and pre-computing saves computation time during forward passes. Then, the transformer layers. The model stacks n-layer blocks of causal self-attention and feed-forward layers. Each attention layer applies self-attention with rotary embeddings, query key normalization, and multi-query attention. Each feed-forward layer applies a nonlinear transformation, specifically ReLU squared activation. This is ReLU of x then squared. It is slightly unusual but works well in practice. Finally, the unembedding layer. This is a linear layer that projects from the embedding dimension down to vocabulary size. This gives largits for the next token. The forward method takes token IDs, produces embeddings, runs through transformer layers, and produces largits. If you pass targets, it also computes the loss. Cross-entropy between predicted largits and actual targets. The loss can be reduced as a scalar average, or returned as a two-dimensional matrix with per-token losses. This flexibility is useful for evaluation. The causal self-attention class. This class implements a single attention head that is causal, meaning it cannot attend to future tokens. In initialization, it creates 3 linear layers: query projection, key projection, value projection. It also creates an output projection that combines the attention results back to the original dimension. In the forward pass, it first projects the input to get queries, keys, and values. Then it applies rotary embeddings to queries and keys. Then it normalizes them. Then it applies multi-query attention. If there are fewer key-value heads than query heads, it replicates the key-value heads to match. This is what lets you have many query heads but shared key-value heads. Then it computes attention scores as the dot product of queries and keys, scaled by 1 over the square root of head dimension. This scaling prevents the dot products from becoming too large and causing training instability. Then it applies a causal mask. Queries should only attend to keys at or before their position. This is crucial for autoregressive generation. Then it applies softmax to get attention weights. Then it multiplies the weights by values to get the output. If there is a key-value cache, it updates it and uses cached keys and values for efficiency during generation. The feed-forward class. This is a simple 2-layer network with a nonlinearity in between. The first layer projects from embedding dimension to intermediate dimension, which is usually about 4 times larger. This is where the model can do nonlinear transformations. Between the layers, there is a ReLU squared activation. ReLU is the rectified linear unit, maximum of 0 and x. Squaring it makes it even more nonlinear. It is a design choice that works well. The second layer projects back down to embedding dimension. With a residual connection, the input is added to the output. This helps gradients flow backward through the model. The attention mechanism explained. Let us walk through the attention computation step by step because this is the key innovation of transformers. You have a sequence of tokens. Each token is represented as a vector. For each token, you compute a query, a key, and a value. These are linear projections of the token representation. For each token position, you compute attention as follows. Take the query for that position. Compute dot products between this query and the keys at all previous positions. Scale by 1 over square root of dimension. Apply softmax to get weights summing to 1. These weights tell you, for this query, which keys are most relevant. Higher weight means more similar. Then you weight the values by these weights and sum them up. This weighted sum is the output for this position. By doing this for all positions in parallel, you get the full attention computation. This is efficient on GPUs because it is mostly matrix multiplications. The attention mechanism is learning what to focus on. In the beginning of training, the attention is random. Over time, it learns patterns. It learns that pronouns refer to previous nouns. It learns that adjectives modify the next noun. It learns to propagate information that matters. The data loader in detail. The function tokenizing distributed data loader in dataloader.py streams data from Parquet files, tokenizes it, and yields batches for training. It uses the distributed data parallel API to ensure that each GPU gets a different subset of data. Each GPU processes DDP rank with step DDP world size. This ensures no overlap and full coverage. It maintains a DEC, a double-ended queue of tokens. Tokens are streamed in from Parquet as they are downloaded, and tokens are popped out as batches are yielded. This streaming approach means you never load all the data into memory. For each batch, it accumulates tokens until it has enough for one training step. Then it reshapes them into a matrix of shape batch size by sequence length. The first column of the previous token and the last column of the target token. It pins the memory on CPU before transferring to GPU. This is an optimization. Pinned memory transfers to GPU faster than unpinned memory. The ADAM-W optimizer. The dist ADAM-W class in ADAMWare.py is a distributed version of ADAM that uses ZRO2 style sharding. In the step function, gradients are first reduced and scattered across GPUs. Each GPU receives its shard of the averaged gradients. Then, for each parameter, the optimizer computes first moment, beta 1 times previous first moment plus gradient, and second moment, beta 2 times previous second moment plus gradient squared. The update is parameter minus learning rate times first moment divided by square root of second moment plus epsilon. This adaptive learning rate is what makes ADAM adaptive. Parameters with large gradients get smaller steps. Parameters with small gradients get larger steps. The learning rate can be scaled per parameter using an LR-mul attribute. This allows different learning rates for different parameter groups, like a lower learning rate for embeddings. The muon optimizer. The muon class in muon.py is more sophisticated. It uses orthogonalization via Newton-Schulz iterations. The key insight is that for matrix parameters, you want updates that respect the geometry of the parameter space. Muon orthogonalized the momentum, meaning it computes a step that is orthogonal, not arbitrary. The zero power via Newton-Schulz 5 function computes an orthogonalization. It takes a matrix G and returns an orthogonal matrix close to G. It does this using Newton-Schulz iterations, a method from numerical linear algebra. In the muon step function, it first computes standard SGD momentum. Then it orthogonalized the momentum using Newton-Schulz. The result is a step that is orthogonal. This is inspired by natural gradient methods, which take steps in a direction that respects the geometry of the loss landscape. For transformers, this often converges faster than standard methods. The engine class. The engine class in engine.py wraps the model for efficient inference. It maintains a KV cache, which stores keys and values from all previous tokens. The generate method takes a prompt in token form and generates new tokens. It does this in 2 phases, prefill and decode. In prefill, it runs the entire prompt through the model at once, computing the cache as it goes. In decode, it generates tokens one at a time. For each token, it runs just that token through the model, using the cached keys and values from previous positions. This is fast because you are not recomputing attention over the entire sequence. Between each step, it samples from the model's output distribution using temperature and top K sampling to add variety. The engine also supports tool use. If the model generates a Python start token, it collects subsequent tokens until Python end, decodes them, and executes the code in a sandboxed environment. The training loop in base train.py. The training script orchestrates the entire training process. First, it sets up distributed training, ensuring all GPUs are synchronized. Then it creates the model, tokenizer, and optimizer. Then it enters the training loop. For each iteration, it gets a batch of tokens from the data loader. It does a forward pass computing the loss. It does a backward pass computing gradients. If it is time to evaluate, it evaluates on a validation batch and logs metrics. If it is time to checkpoint, it saves the model. It updates the learning rate schedule, warming up, staying constant, then cooling down. It does an optimizer step, updating all parameters. The loop continues until the target number of flops is reached. Flops is floating point operations. This gives a hardware-independent measure of training progress. The fine-tuning process in chat sft.py. The fine-tuning script is similar, but operates on conversation data. Instead of streaming data from Parquet files, it uses the task mixture class to create a mixture of different tasks. It samples uniformly from this mixture. For each batch, it formats the examples as conversations with user and assistant messages. It renders these as token sequences with masking, so the model only learns to predict assistant tokens. The training loop is the same. Forward pass, compute loss on masked tokens, backward pass, optimizer step. Learning rates are typically lower than during pre-training. The model is already well trained, so smaller steps are better. The reinforcement learning in chat rl.py. The RL script generates multiple completions for each problem. For each problem, it uses the engine to generate multiple samples with high temperature to encourage diversity. It evaluates each sample by checking the final answer. It computes advantages, the reward for each sample minus the average reward. This centers the rewards. Then it runs a training step on this batch. The loss encourages the model to predict continuations that have positive advantage and discourages negative advantage continuations. The advantage is computed per token, so the model learns which tokens in good continuations are important. The evaluation functions. The evaluate BPB function in losseval.py computes bits per byte. It iterates over a batch, computes the loss for each token, and normalizes by the number of bytes each token represents. This vocabulary-independent metric is useful for comparing models with different tokenizers. The core eval module runs specific benchmark tasks. For each task, it renders the task as multiple-choice questions or fill-in-the-blank questions. For multiple choice, it computes the log probability of each possible completion and selects the one with highest log probability. For fill-in-the-blank, it prompts the model to generate the blank and checks if the tokens match. All of this runs distributed so you can evaluate quickly. A note on code philosophy. Now let us reflect on the code structure and why it is the way it is. NanoChat is intentionally small. There are no giant configuration objects, no factory patterns, no inheritance hierarchies. Instead, the code is straightforward and direct. A file does one thing and does it well. GPT.py is the model. Dataloader.py is data. Training scripts are training. A function is usually short and clear. You can read it and understand it in one sitting. You can modify it without worrying about breaking distant abstractions. This is by design. The philosophy is, keep it minimal, keep it hackable, keep it clear. When external libraries are used, they are minimal. PyTorch for neural networks. Hugging Face tokenizers for tokenization. That is mostly it. No cutting-edge frameworks that promise to make everything better but hide important details. The code prioritizes clarity over cleverness. Where there is a choice between a subtle Python idiom and a slightly longer explicit line, explicit almost always wins. This philosophy matters. It means you can take this code, understand it completely, modify it, and make it your own. You are not fighting a framework. You are working with transparent, understandable building blocks. The Feynman spirit. We should end by thinking about why understanding matters. Richard Feynman said, "What I cannot create, I do not understand." This codebase embodies that principle. To truly understand language models, you do not just read papers. You implement them, you train one, you see what works and what does not. You hit bugs and learn to fix them. NanoChat makes this possible. It is complex enough to be real. You are really training a neural network. You are really generating text. You are really deploying it. But it is simple enough that you can hold the entire system in your mind at once. When you run the speedrun script, you are not just watching numbers scroll. You are watching a computer learn the patterns of language. You are watching it build understanding from data. You are participating in one of the most fascinating phenomena in modern computing. The code teaches through simplicity. Each design choice has a reason. When you wonder why the model does this, you can read the code and find out. You will not be lost in layers of abstraction. This is the heart of the project, to make state-of-the-art AI accessible not just in the sense of affordable, but in the sense of understandable. Your journey forward. Now that you understand the design and philosophy, what can you do? You can run it yourself, train a model on your own data. Fine-tune it on domain-specific content, modify the architecture, try different activation functions. Experiment with different optimizers, change the tokenizer. The codebase is yours to hack, you can extend it. Add support for other input modalities, build a different interface, integrate different tools. The minimalism means there is room for your ideas, you can study it. Spend time reading each file, build a mental model of how the pieces fit together. Use it as a reference for your own projects. Most importantly, you can learn from it. This is what modern AI looks like when explained clearly, not through blog posts or papers but through code that works and makes sense. The code is the documentation. In NanoChat this is true. The code is beautiful. The code is clear. The code is educational. You have now seen the transformer architecture from multiple angles. You understand how data flows through the system. You understand how the model learns, how you can fine-tune it, how you can align it with human preferences using reinforcement learning. You understand how to evaluate it on diverse benchmarks. You understand how to serve it to users. You understand the philosophy. Simplicity is a feature. Ideas matter more than engineering. Pragmatism wins. Accessibility is paramount. Go forth, build, understand, create.